Welcome again. Having looked at pipelining, I'd like us now to see the challenges, one of the greatest challenges that faced pipelining architecture. When you talk of pipelining, it means before an instruction is over, there is no cycle that is lost. If an instruction is in the execute, the first instruction is in the execute cycle, the second instruction is in the first cycle. We've seen how buffers help in implementing this pipeline architecture. Having seen that, one of the challenges that comes in is when one instruction depends on the other. For instance, what you're seeing here, A is a result of 3 adding A to 3. So that means A is 5, for instance. 5 plus 3 is what is going to be assigned to A again. However, the instruction B is dependent on A. And therefore, if these two instructions were to be executed in parallel like it happens in pipelining, that would mean, or almost in parallel like it happens in pipelining, it means that because the second instruction depends on the first one, somehow the second instruction has to wait for the first one to complete before it can also complete. That is a constraint in is a dependency constraint in pipelining. And I don't want to be in so much of a do. In the second case, you can see there is no relationship. Both of them are depending on C, but as much as they are depending on C, C doesn't change. C doesn't change, and therefore they can comfortably both of them use C at the same time. They can be executed in parallel. That is what the narrative there is talking about. So those dependencies can be avoided by the addressing we make, but sometimes it's inevitable. We have to go through those dependencies. I would like us to look at processor architectures and processor performance enhancement designs. So we have one that we call the reduced instruction set computer, and another one which is called the complex instruction set computer. The reduced instruction set computer is designed to be very fast. It's a processor that is based upon this concept to use few instructions, which would require fewer transistors and make them cheaper to manufacture. By reducing the number of transistors, of course, and instructions to only those most frequently used, the computer would get more done in a short amount of time. RISC supporters argue that it's a way of the future, producing faster and cheaper processors. Instructions are executed over 4 times faster, providing a significant performance boost. If you want to view what happens within a RISC machine in pipelining, then see that the idea of producing faster chip, they have to use a number of techniques including pipelining. We know that the performance of pipeline system depends on the time it takes only for one stage to be completed. In a typical pipeline RISC design, each instruction takes one cycle for each stage, so the processor can accept one instruction per clock. And of course, we had mentioned earlier that pipelining does not increase the speed, it increases the throughput. So the RISC or reduced instruction set computer has the following characteristics: a small instruction set, simple instructions to allow for faster execution, that's fewer steps, and both operands should be available in register to allow for short fetch time. The generating of large number of registers, only read, stroke write, or load and store instructions should access the memory. Simple addressing modes are followed in order to allow for faster address computation. Fixed length instruction will be few, and aligned views to allow for faster instruction decoding. Complex tasks are left to the compiler to construct for simple operations with increased compiler complexity and compiling time. Simpler and faster hardware implementation, especially suitable for pipeline architecture. RISC seems to be very good for pipeline architecture. The advantages include speed, simpler hardware, shorter design cycle. Now, if we compare that with complex instruction set architecture, we'll discover that this complex instruction set architecture has a large instruction set, complex operations, complex addressing modes, complex hardware, long execution time, minimum number of instructions needed for a given task, and easy to program or simpler compiler. Unfortunately, this is what most of the computers we use today have, CISC instead of RISC. And of course, you can see from that comparison that CISC has a small number of instructions, but large cycle per instruction and large clock time than RISC. So it will be a temptation that we would go for RISC instead of CISC.